Now that we've done a lot of work with exponents, let's look at exponential functions. Here's the first exponential function that I'd like you to consider, y equals 2 to the x. I would like you to create a table of values and a graph for this particular function. So take a moment and do that now, please. So I'm going to choose some values of my independent variable, or x, as -2, -1, 0, 1, and 2. Those are values I'm just choosing. Remember, I could have chosen other values as well and extended my graph further. So let's start with 2 to the -2. We're going to apply our knowledge of how to manage negative exponents, and I know that I can then rewrite that as 1 over 2 to the +2, or 1/4. I'll do the same thing with the rest of the powers. So here are the points that I have so far. As I move to the right of the graph, I notice that 2 to the 1 is equal to 2, 2 squared is equal to 4. If I wanted to even extend that in my head, I know that 8 would be the next point that would lie on my function. And because I'm only choosing these values, but I know they could extend in either direction, I'm going to put an arrow on to the right side of my graph. Let's take a look at to the left of 0. When x is equal to -1, I know the value of my function is going to be half. When x is equal to -2, it's going to be 1/4. Hopefully you can see that we are moving and having the values. So if I had extended this to -3, I would have had 2 to the -3, which would have been equal to 1 over 8. As I would continue to move to the left, I would have 1/16, 1 over 32, and so on. Of course, it just gets more and more difficult to plot simply because the fractions are so small. Hopefully we can see, however, that my value of my function would continue to get closer and closer to 0, but it would never actually touch that. That might occur to some of you to be very similar to something we saw when we dealt with reciprocal functions. Since this exponential function will continue to approach but never touch the x-axis, we say that there is a horizontal asymptote on that axis. So in this situation, the horizontal asymptote would be at y equals 0. If I wanted to state the domain and range of this particular function, I would say that the domain belongs to the reals, and I would say that the range also belongs to the real numbers. However, it only exists where y is greater than 0. Notice in this situation, it's not greater than or equal to 0 because our function never actually equals or touches the horizontal asymptote where y is equal to 0. Another really important part of this function that we might want to note is the value of the y-intercept. Notice here the value of the y-intercept is 0, 1. And that might be interesting to us because we might notice that that happened because we had our base of our exponential function 2 raised to the exponent 0. Notice that it really wouldn't matter what this base was. If I raise any number to the exponent 0, I'm going to get a value of 1. So if I were to graph a different function such as y equals 3 to the x or 4 to the x, I'm always going to have a y-intercept of 1. That's one of our characteristics of our exponential functions. Now let's explore what happens when we change the base of our exponential function. On the previous page, we graphed using a table of values y equals 2 to the x. I want you to take a moment now and graph y equals 3 to the x and y equals 4 to the x. Before you actually start writing something down, I want you to make a guess, make a hypothesis in your head about how the graphs of the latter two functions might compare to the graph of the original function that we graphed. So we could go ahead and create a table of values for each of these three functions. In an effort to show you in an efficient way, I'm showing you a screen capture from Desmos. You'll notice that the red function is the one we graphed on the previous page, and that's y equals 2 to the x. You'll see that the blue function is y equals 3 to the x, and the green function is y equals 4 to the x. So you'll notice that as the base of the function increases, the function grows more quickly. We can think about this as the first function, y equals 2 to the x. Each time, each stage of our graph, the value of the function is doubling. For y equals 3 to the x, for each subsequent stage of the graph, the function's value is tripling. So hopefully it makes sense that y equals 4 to the x, the function is increasing at a much greater rate, so it's growing faster. What you will notice is what we discussed on the previous page. Notice that all functions, however, share the same y-intercept, which is 0, 1. Regardless if I have my base of 2, I'm going to get 1 as my y value when x is 0. The same thing happens when my base is 3 or when my base is 4. Let's explore now what happens when instead of having a whole number as our base that's greater than 1, we now have a fractional value for our base that's between 0 and 1. Keeping in mind that we said on the previous screen that the base really told us how quickly our function was growing, try to see if you can make a guess before you actually go ahead and graph this. Make a guess at what this graph might actually look like if the base is equal to 1/2. For this one, I think it would be wise for you to go ahead and actually draw your table of values and your function on your own Cartesian plane again. So take a moment and do that now. So I started by drawing my Cartesian plane and just substituting in the values of x into the y equals 1/2 equation. Hopefully we will recall that when we're trying to evaluate these powers, if we're taking a negative exponent and applying it to a fraction, I can rewrite that as 1 over the value with a positive exponent, or I can take the reciprocal. So that could just become 2 over 1, which would be squared, and then the values would be as we see them here. So here are our points plotted on our Cartesian plane. What you're going to notice is that our graph is somewhat flipped or reflected horizontally across the y-axis. Similarly to our y equals 2 to the x function, as our x values change, at some part of the graph they get closer and closer to 0, but don't actually touch 0 in terms of the y. So if I'm to extend this graph to the right, we'll notice that I would get 1/2 cubed, which would be 1/8. If I were to continue this, I would get 1/116th, 1/132nd, and so on. So we're continually approaching but never touching the x-axis. We also note here that because we had the base raised to the exponent 0, we have a y-intercept of 1. Our domain and range really match and coincide with what we said they would be for y equals 2 to the x. So what I'm hoping that you will notice here is that when our base is a number between 0 and 1, we notice that instead of our function showing growth from left to right across the domain, in this situation, our function is showing exponential decay. So the reason why we're looking at both growth and decay is because there are so many different applications in the world that use these different types of functions. Exponential growth, we could look at interest growing, we could look at population dynamics and population growth. For exponential decay, we could look at things such as radioactive isotopes decaying, like carbon-14 dating. Many medical tests that use radioactive isotopes, the way that the isotopes decay deal with this exponential decay. So a lot of the math that we're learning about now has very real applications in the real world. So several other opportunities to just extend your thinking. I want you to consider what the graph y equals 1 to the x might look like. I want you to think about that carefully before you use Desmos to check any sort of hypotheses. I also want you to try to think about and picture what the graph y equals -2 to the x would look like. And in this situation, notice that I'm putting brackets around the -2, so I'm implying that the negative sign is part of the base there. So take a moment and just think about that. Let's start with y equals 1 to the x. When we use a table of values or even Desmos to examine what this function looks like, we notice that as we take our 1 and raise it to any exponent, we're always going to get 1 as our answer. So we really just get a horizontal line here. So notice that that does not look like an exponential function. It's showing neither exponential growth nor exponential decay. So this tells me that if I want to have an exponential growth or decay function, I'm not going to have my base be just simply equal to 1. It's going to be larger than 1. So we notice here that when our base is negative, the value of our y, the value of our function, is going to move back and forth between being positive and negative values. If you consider when you have a negative base and an odd exponent, so if that were to be a 1, it would be -2 to the 1, which is -2. But as soon as I make this exponent into a an even value, such as 2, I'm going to get -2 squared, which is going to be a positive value, or 4. What this means is that the value of the function will oscillate back and forth between positive and negative values. So notice that too is not going to show any sort of smooth exponential growth or any sort of smooth exponential decay. For that reason, I'm going to state that my base is not allowed to take on a negative value either. So here's a summary of the different properties of exponential functions that hopefully you've been able to explore a little bit. So an exponential function, and the general form of that is going to be b to the x. So this is where it's a little bit different than the other parent functions that we've had. When we've done parabolas, when we've done absolute value functions, we've had a single parent function that we moved around. In the case of exponential functions, it's possible that we have many parents, but they all share common characteristics. So in a particular graph, my parent might be y equals 2 to the x. My parent might also be y equals 3 to the x that I'm transforming. Similarly, I might have an exponential decay curve where I transform y equals 1/2 raised to the exponent x. So my parent might be a little bit different, but it will share the characteristics that we've listed here. We must have our base as a positive value. Hopefully we've established that on the previous slide. The domain is going to be an element of the real, so it is going to extend from left to right across the Cartesian plane. The range of the original parent function, regardless of the base, is going to be greater than 0. It's going to lie above the x-axis. No matter what the base is, the y-intercept is going to be equal to 1. And that's because anything raised to the exponent 0 is equal to 1. The asymptote of the function is going to be the x-axis, or y equals 0. Again, that doesn't change depending on the value of your base. If our base is greater than 0, so if it's a number like 2, 3, 4, or a fractional value greater than 1, like 1.2, 1.4, they would be included there as well, then we know that exponential growth is being expressed by that function. If instead the value of the base b is a fraction between 0 and 1, like 1/2, like a quarter, like a third, like the value 0.9, any value that is between 0 and 1, we notice that our function will display decay or exponential decay. So those are the basic properties of exponential functions. As we move forward, we're going to look at taking each of these parent graphs and transforming them in much the same way that we've transformed all of our other functions in the course.